So here we are at lecture 5C, and we're going to start talking about things that are called SALCs, which stands for Symmetry Adapted Linear Combinations. And this is what's going to make our life a little bit easier when we're looking at molecules that are larger than diatomics. So what is a SALC? Well, it's what we use when we have more than two atoms in a molecule. Now we know that molecular orbitals are spread throughout the molecule and that atomic orbitals of any and all atoms in the molecule can get involved in forming those molecular orbitals. So what determines, one, how a molecular orbital forms, where does it form, what atoms are involved, what molecular or what atomic orbitals are involved? SALCs help us answer all of these questions. One of the fundamental principles of molecular orbital theory is that molecular orbitals form from atomic orbitals with similar energies and the same symmetries, and that becomes very important. Similar energies and the same symmetries. So we can use our character tables and the group theory that we just learned to determine a molecular orbital diagram for molecules. So we're going to look at water first because it's a nice, simple molecule. It only has 3 atoms, 2 hydrogens, and we just have to deal with the S and the P orbitals on the oxygen. So we refer to molecules like water as just an AXN, or for water it would just be AX2. So it would be like OH2, where A is our central atom, so that would be the oxygen in this case. And then we have the atoms that are attached to it. And one term for those are called pendant atoms. And for water, these are bent away. So what we're going to do is make linear combinations of atomic orbitals that are compatible with the symmetry of the molecule. And then we're going to form molecular orbitals using the atomic orbitals of the central atom and the SALCs of the pendant atoms that have a similar symmetry and energy. It sounds a little complex, but we'll get through it step by step. So the first thing that we need to do for a molecule is to identify our point group using the flowchart that we had last week. We see that water has a bent geometry, and when we go through our point group, we find it has a C2V point group. Next, we're going to want to make SALCs, our symmetry-adapted linear combinations of the pendant atoms. The oxygen orbitals are not part of the SALCs. We only make SALCs of the pendant atoms. So here we're only going to involve the hydrogen atoms. So the hydrogen atoms themselves have only s orbitals. And we know that the bond from the hydrogen is going to go towards the central atom, towards that oxygen. So we can treat it a little bit like a vector pointing towards the oxygen atom. The bonds don't go anywhere else other than between the hydrogen and the oxygen. And so because we're looking at the s orbital on the hydrogen, that's why we can treat it like a vector and help us look at what our traces for the different operations are going to be. So here we have something like this. So we have our hydrogen here. You can think of it as moving this way towards the oxygen, and this one going this way towards the oxygen. Again, we don't care too much about it being a vector. We're not going to do any kind of vector operation on it, but it helps us with the symmetry and the concept of symmetry. Okay, so here's our molecule here. We're going to distinguish the 2 hydrogen atoms from each other, H1 and H2. We want to make sure that we keep that identity separate so that we can see, did the hydrogens change place, because that does affect what kind of symmetry operation, or what the symmetry operation has done to the molecule. So we need to find something that's called a reducible representation of the symmetry of the orbitals that are on the pendant atoms. So we had irreducible representations prior. What we're going to find first is a reducible representation, and then we'll look at what the irreducible representation might be. So here's our just a table that we're going to go through and fill in. We have our C2V symmetry. The operations in C2V is an E operation, the identity. Water has a C2 axis, and that's indicated in the C2V character table, we have a sigma V and a sigma V prime. We saw both of those in the last part of the lecture. So gamma SALC just means what are the traces for my different operations. And so here's our character table here. This is a little bit more complete than what we saw earlier. Again, we see the sigma V and the sigma V prime, and they also give us our axes there. We see some different things over here. We have an X, a Y, and a Z. If we had p orbitals on here, and we do on the oxygen, we'll take a look at those in a little bit. We see that the Z orbital transforms as an A1 symmetry, an px orbital is as a B1, and the py orbital is a B2, which is what we found earlier. So these are for simple ones or for rotations in the Z, Y, or X. These are our quadratic functions. So if we had d orbitals, we would be looking at these, but we don't have that in this case. We don't have to worry. This H up here is what we call the order of symmetry. And all that H value is, where that 4 comes from, is it's the sum of the coefficients in front of our operations here. And so this is 4 because we have a 1, a 1, a 1, and a 1 right here. And so H is 4. The larger the H number is, the more symmetric a molecule is. We also use this number to do some calculations, and we'll see that a little bit later on this slide. Now let's take a look and fill in our values here. So really what we're doing is we want to see how many of our hydrogen atoms stay the same when we do an operation given in our row right here. So if I do the identity operation, the molecule doesn't change. And so H1 becomes H1 and H2 becomes H2. And so I have 2 of my vectors remain exactly the same. If you want to look at it in terms of a matrix, so we would have our H1 and H2 here. So we have 1 and 0 because that's our H1. 0 times 1 times our H2. And that gives me H1, H2. For the operation of E, the H1 transforms as H1. The H2 transforms as H2. And so that's why I get a 2. The trace here, mathematically, is right here. And that's where we get our 2, is that sum. We're not going to go through all of that for each one. If it's confusing to you, you can certainly take a look at that, or if you want some help with that, I can go through that with you. Okay, so let's look at the C2 operation. What's going to happen with the C2 operation? Well, for the C2, I'm going to rotate this molecule around that axis. And so the H1 is going to come over here, and the H2 would come over here. And so neither the H1 nor the H2 have maintained their position, so I have different vectors in the same locations. So that has a trace of 0. If I do my sigma V, so my sigma V, I would have a plane right here, like that. So the H1 would reflect to H2, and this H2 would reflect over here. So that's also going to give me a 0 because neither the H1 or the H2 are in the same location. And then for my sigma V prime, this is a mirrored plane that's here. It's in the plane of our screen. And so the H1 would reflect just on the other side of the H1, and the H2 would reflect onto the other side of the H2. And so my sigma V prime would have a 2 trace. Now, what we want to do, this is a reducible representation, and we want to what's called deconstruct this in terms of the character table. And so what we're going to do is say we want to know which of these operations describe the symmetry of these H1 and H2 orbitals, these SALCs, when we put them together. So what we need to do is figure out what combination of all of these functions in here add up to this character table. Okay, so there's a couple of different ways that you can do this. You can do it by inspection, where you just figure out what adds up, which of these functions add up to equal this, and there's only one possible combination that will do so. And so you can figure that out. It's a little bit like a number puzzle. This is a fairly simple system, and so it's not too bad. The other way that we do this is through something called the the projection operator. And for a projection operator, what we do is we take each of our functions here. So we'll start with A1, and we take 1 over h. So here our h is 4. And then we're going to multiply it by a lot of different numbers. And we've got 2, 1, and 1. And where these 2, 1, and 1s come from, the 2 comes from here. The 1 of those 1s comes from here. I got to figure out which one is which. Yeah, that one. From there. And then this one, let's pick a different color. We'll do blue. This blue comes from here. Okay, so we just go through all of those and see what we end up with. Okay, so we have 2 times 1 times 1. That gives us 2. And then our next one, notice that we have, for C2, we have 0. So that gives us a 0. And then a 1 and a 1. Oh, that should be blue. Circle the number there. There we go. Okay, and then we have 1 and a 1 again, but we have another 0 right here, so we get the 0 here, so those terms don't factor in. And then I have another 2 and a 1 and a 1, or a 1 and a 1. So when I add up 4 and or 2 and 2, I get 4, and 4 divided by 4 gives me 1. So there is an A1 in this molecule. If I look at A2, I have 2 plus 0 plus 0 plus minus 2. Okay, so the 2 and the minus 2 cancel out, so I get 0. So 1/4 times 0 gives me 0. So none of these SALCs have A2 symmetry. I go to the next one, B1, and I apply the same 2, 1, and 1. I have 0, 1, minus 1, 0, 1, minus 1. And then I have 2, 1, minus 1. So I have 2 minus 2. So those are 0. And so I have no B1s. And I go to the next one, and I have 2, 1, 1. So I have 2 here. These 2 go to 0. I have another 2, 1, 1 here. And so I have 2 plus 2 gives me 4. 4 divided by 4 is 1. And so we can summarize the symmetry of the SALCs as I have an A1 plus a B1. Now, what do we do with A1 and a B1? Well, these books that have the character tables in them will also have representations of the SALCs for different symmetries with different representations. So we would see a diagram that looks something like this. Okay, and so we know our water molecule is a C2V geometry. There's a C2V point group. I have an A1 and a B2. So an A1 SALC looks like this. So this would be my hydrogen here. This is my other hydrogen. This is the central atom there. So I have my atom there and an atom there. Okay, and then here I have a B2. So here they're just different phase. So I have one different phase here. So this is one of the other hydrogens. The oxygen is not involved. And then my other pendant atom here with a different phase. So these are the SALCs for the hydrogen atoms. Conservation of orbitals still applies, just like we've always had in molecular orbital theory. If I'm bringing in 2 atomic orbitals, I have to have 2 SALCs, because these also represent orbitals and orbital arrangements. So if I bring in 2 orbitals, I can only have 2 orbital arrangements. Now, what are we going to do with these? So here we have our SALCs, and we can set them, their energy, based on a hydrogen 1s. These are nothing more than the hydrogen 1s orbitals on the hydrogens. And so they are going to have the same energy, the ionization energy, as a hydrogen atom, so about 13.6. On the oxygen, we don't worry about the 1s orbitals on the oxygen because they're not valence. We're only going to concern ourselves with valence. We have the 2s here, which is just going to be like just the regular s orbital here. And then we've got our two px, py, and pz. I will say that the diagram that this came from did not orient the x, y, and z in the same way that I would orient it for the molecule. So just bear with me on that. Now, you might say, can't these two hydrogen orbitals interact here? Well, no, they can't. They're too far. They're too far apart to interact in any kind of bonding way. We will see a little bit later in the lecture where they can have an impact on the energy, but nothing really significant. So we're not going to worry about it at this point. For right now, just think of these. These don't sit there and make a bonding interaction, and these don't make an anti-bonding interaction because they're going to want to focus with the oxygen atom for now. If we go through and do the same type of filling out of a trace table, reducible representation with our atomic orbitals on the oxygen, we would find that the 2s orbital has an A1 symmetry, and we would find that the 2px, 2py, and 2pz's have a couple of different symmetries. They have an A1, a B1, and a B2. We can also just look this up in the character table. Remember, I pointed out that you have those X, Y, and Z labels towards the right-hand side of the character table, and they will tell you what symmetry each of those orbitals has. And so that just makes up these labels here. Okay, so these tell us what symmetry each orbital has, and we also have the symmetry of the SALCs. And remember what we said is that orbitals can only interact if they have a similar energy and the same symmetry. They must have the same symmetry. So let's combine some things with the same symmetry. Well, the first thing that we see is that we have an A1 here for the S, and we have an A1 here for our SALCs. And so they would look like this. Remember, we have our bent geometry, so we have H, O, H. And so we have our hydrogen here, and our oxygen here, all in the same phase in a bonding interaction. And so that's an A1. Don't pay any attention to those labels just yet. Now, if we're going to interact in a bonding, they also have to interact in an anti-bonding. And the easiest way to do the anti-bonding is just to change the phase of that central atom. So we have that here. And so we have an anti-bonding between these two orbitals and anti-bonding between these two orbitals. And so that's going to raise the energy considerably. So this orbital is going to be very high in energy. If we look at the next one, we see our other SALC is a B2 symmetry, and that's the one that has these two different phases. And that can interact with one of the p orbitals, and it's actually going to interact with the py or the px. We'll say the py because it lines up really well with what we did earlier. And so that's our B2 symmetry, and we see it's got a dark one and a light one, so we'll overlap the dark and the light between the p orbital on the oxygen and the SALCs of the hydrogens. And so we have a nice bond right there, we have a nice bond right there, and because we have bonding interactions, we're going to drop in energy there. And this molecular orbital also has a B2 symmetry. Just because we brought two B2 orbitals together does not necessarily mean that the molecular orbital will be B2. It happens a lot of the time, but you do actually have to look at how this molecular orbital is made up and go through the operations to make sure that it is in fact B2. Notice also that my atomic orbitals have capital letters. My molecular orbitals, by definition, will only use lowercase letters. Okay, well, just as before, because we have a bonding interaction, we also have to have an anti-bonding interaction. So again, we're just going to change the phase on the p orbital for the on that oxygen atom in the center. We'll leave the phases of the SALC the same. So now we have an anti-bonding interaction here between the S and the P, and another anti-bonding interaction between this S and this P. So that's also going to go up considerably in energy. The last one we have is this guy here, the interaction between the p orbital. So this would be our pz orbital on the water, and our A1 SALC. And so your PZ does have an A1 symmetry, and we still have the A1 symmetry here. There is, however, very little electron density present in the SALC here, with the for the hydrogen atoms. Bulk of that electron density is going to be in the low energy here. So this is extremely low bonding orbital. We actually represent this as a non-bonding orbital and represents one of our lone pairs on water. It has just a little bit of S character. Calculations show that we just have a little bit of S character there. Now, the one set of orbitals we haven't dealt with yet, oh, we do have to have an anti-bonding here as well. Actually, we don't, because it's essentially non-bonding, and so we don't even put in an anti-bonding because we don't really consider it bonding. We have one symmetry over here in our p orbitals that isn't matched over here, and so the B1 cannot form a bonding interaction with anything because it doesn't match the symmetry of anything else over here. And so this B1 becomes non-bonding because it can't overlap. Now, if we take a look at occupying our orbitals with electrons, we know that oxygen occupies like that. Our SALCs would occupy like that. We have one electron in each of those s orbitals. So we have a total of 6 and 8 electrons. And so they're going to fill in like this. Still follow Hundrel. So they'll follow something like that. So these become our bonds between the hydrogen and the oxygen, and these two become our lone pair on the oxygen. If we were to fill out an electron configuration, we would say 2A1, 2, 1B, 2, 2, 3A1, 2, and 1B, 1, 2. And that's how we would write that electron configuration.